Hi, this lesson is all about templates, and we'll start this lesson off by talking about function templates. A function template is a generic function that can operate on multiple types. This will make more sense as we move along throughout the rest of the video. C++ is a strongly typed language, right? So variables need to have a specific type. You cannot just have variable x and variable y. X and y need to have a type, so x could be an int, y could be a float. And by using function templates, we can write abstract functions that work on any type, whether the type is explicitly specified by the programmer when calling the function or deduced by the compiler. How is all of this useful? Well, instead of overloading a function multiple times to work with multiple types, we can define a single function template. Function templates allow for algorithm abstraction because, let's say some other programmer comes along and uses your functions. Again, they are not necessarily interested in how the function is implemented, they just want to use it. And function templates have the same functionality, or in other words, the same algorithm, so they do the same thing, and sometimes you want those to do the same thing on different types. So some other programmer can come along and use the function that you've defined, the function template, maybe explicitly specify the type, float or int, and they'll get consistent results. They'll get the results that they would expect from that function invocation. The function template prefix is going to indicate to the compiler that the following function is a template. You can see the syntax for the template prefix in the example below. You use the template keyword, followed by opening and closing angle brackets. Then you can use type name or class, followed by a type parameter. The type parameter is going to sort of accept, almost like an argument, the particular type that you want. If this doesn't make sense right now, don't worry about it. We'll talk about it in more detail as we go along. And then following this template prefix, we move on to the function prototypes. We have the return type, which again can be void or int or whatever you need, followed by the function name. Then of course you have your formal parameters. Your formal parameters can use the type parameter. I would like to note that you can use class instead of type name here in the template prefix. I'll show you a few examples in a later slide. In this example we use type name, so that type name keyword is going to suggest that the template parameter t is a placeholder for a type. When the function is invoked, the compiler is going to replace every instance of t with the type argument that is explicitly specified by the programmer or deduced by the compiler. So that if you specify, okay, I want this function to use integers or floats or doubles, that t or type parameter is going to get replaced by whatever you specify. So again, integers, floats, and so on. And of course, sometimes you want your function to return that type. That is why you can also use that type parameter, in this case t, where you specify the return type for the function. And then you can move on to use that formal parameter in the body of the definition of the function. If you separate out the declaration and the definition of your template function, then in each case you are going to specify the function template prefix. We can see the example here. In the first example, we have the function template declaration syntax. You have the function template prefix, followed by the function declaration or prototype. That ends off with a semicolon. Then if you do a function template definition, once more you have the function template prefix. That is where we specify the type parameters between those angle brackets. And following that, you are going to have the function definition, which of course includes the body of the function and the function prototype or header. As I mentioned previously, the return type of your function can also be the type parameter. So in this example, the type parameter is t. You can actually have multiple type parameters, but we'll talk about that later on in the video. I would like to mention in the function template prefix where you specify the type parameters, you can use either the type name keyword or the class keyword. I prefer the type name keyword, but it's very common to see the class keyword being used here. When the template function is invoked for the first time with a specific type argument, the template function is instantiated by the compiler. For function calls to be resolved at compile time, the compiler generates as many function definitions as needed based on the type arguments provided to the template parameters. And what is this instantiation? Well, template instantiation is the process in which the compiler generates a function from a template function. So function templates are just that, they are templates, and the compiler is going to generate actual definitions based on our function invocations and the types that are provided, and it will only generate those definitions that are needed. So it's not going to generate a definition with a float if we never use floats. Let's say we only call the function with an int type argument, then the compiler is only going to generate that single function definition with an integer type. Okay, so template functions are instantiated or generated only once, and then subsequent calls to a function with matching type arguments will invoke the already generated function. Since template instantiation is done at compile time, we get type checking before the program executes. Here's an example of a function template instantiation. We have the template function definition at the top. We have template, and between angle brackets we have type name t. The return type for the function is going to be void because this is a print function, so we call it print. And then for the formal parameters, we do t formal p just for some formal parameter, and then we do cout formal p. Then we do the function invocation in main, so we do print. We explicitly specify the int template argument following the function name, in this case print, so we do print the angle bracket int, then the parentheses, and we pass in 55 for the argument to the formal parameter, and in that all for the semicolon. Then what's going to happen? Well, the compiler is going to generate a function in which each occurrence of t is replaced with int. In this case, we only use t once, so that's going to generate void print, and then the single formal parameter is going to be of type int. A quick example on how we would use or invoke a function template. In the main function here, I do the print function call, the opening and closing angle brackets, and I specify int. So I specify int explicitly as an argument, and that will get accepted by the template parameter, and then I pass in some value for that function, such as 55. The final print function call is similar to a regular function call, and you can see in this case, an implicit integer template argument will be supplied to the template parameter. So in other words, the compiler is going to deduce which type to use. Let's look at a simple use case. I have this simple example, this void print function that I overload a couple of times. In the first definition, we have void print, and the formal parameter is an int. In the body for each one of these, I'm simply going to do cout formal p for formal parameter, so I simply print that out to the console. In the second definition, in the overload, formal p is of type char, and in the third definition, formal p is of type double. In main, I call those functions, so I do print 33, print h, so that is a character, and then I do another print where I pass in this double or float value. This could also have been a float, and then we can do if right here. If I build around that works fine. We get 33h and that float or double value. I can already see some of the problems that we'll have. If I hover over this error is about the fact that the argument is of type double. So if I Ctrl B to build this, you'll get a failed. You'll get an ambiguous call to that overloaded function. So what we have to do now is, we either have to change this to a double again, or we have to provide another overload. And let's say we want to use this version with the float. Then of course, as before, you can do this right here, float. And if you hover over this, it will actually show you a float. If I remove F and I hover over here, it will show you double. But the point with this is it's a really simple function. What if it was quite complex? We may have multiple formal parameters. We may do quite a bit of computation in the body of the function as well. And notice each time we overload the function, the body is the same, right? And when we duplicate code like this, that should already be a red flag for you. And at that point, you should start thinking about how you can refactor the code. And we can basically clean this up or refactor it into a template function instead. One final thing I'd like you to think about is, what if you had custom types such as a class or a struct, right? And we want to pass that in. Again, this is a really simple sort of demonstration, but let's say we have some class entity that we want to pass in, and that class entity has an overloaded stream insertion operator. Then we cannot pass it in here because we don't have an overload with a formal parameter, which is a type of entity. So what does that mean? Well, now we'll have to go and overload the function once more. Then later on we may add a struct, and again we may provide an overloaded stream insertion operator for that. Let's say that's some vector struct or some player character or something like that. We want to pass it in here to print the stats of that out, or the state of that. This could have been some log function as well. Programmers often have some sort of helper function. Well, this is no good because each time we go and define a new user-defined type, such as again a class or a struct, then we'll have to go and overload this print function, and that is no good. So instead we can use template functions. I have a quick simple example of a template function, void print. In the template prefix we have the template keyword, we have the opening and closing angle brackets, then we have type name. You can have type name or class right here, and then we are using t. T is basically the type parameter, and that is going to accept the type that we pass in basically. So let's say we pass in int, then t will be int. If we pass in double, then t will be double. If we pass in a char, then t will be a char. Then the formal parameter for this function, I'll just call that formal p, p1, or just p. Since in this example we only have one formal parameter, I'll just call it formal p for formal parameter. And what type is that going to be? Well, again, it's going to be t. so whichever type we specify when we actually call the function, and then all I'm going to do is I'm going to print out formal p. So whatever the value is of that argument, I'm going to print out. This is the basic syntax for how we're going to call or invoke the template function. You have the function name, followed by these opening and closing angle brackets, and then followed by the parentheses. The angle brackets are going to accept the argument for the type parameter, so in other words for t, in other words the argument is going to be the type. So let's say int. As usual, you're going to provide an argument for the formal parameters. Let's just do something like 55. What function do we call? We call the function print. We specify the type int. You can think of this as an argument which is going to get accepted by the type parameter. And then between parentheses, we specify the argument for the function, which is going to get accepted by the formal parameters, in this case formal p right here. And since we specify integer here, this formal p is also of type int. If we build and run that works fine, we get 55. Now we'd like to note that you can call the function in this way too, so without specifying the type right here, it's going to look at the type and recognize, okay, that's an integer, and then it's going to generate an integer version of that function for us. Build and run, and that should print out 55 twice. And of course you can specify or use the other fundamental types such as characters, doubles, floats, and so on as well. It prints out 55 twice, h twice, and then those double values as well. As you can see with these examples, we don't necessarily have to provide an argument, the type argument basically, for this type parameter. I prefer to provide the type and be explicit in that way. That also makes it easier for the reader, in other words some other programmer that comes along, that they'll go through and read the code. At a quick glance they'll simply notice, okay, these are template functions. For an exercise, I'd like you to write a function template that is going to return the smallest of two values. So in other words, it's also going to return that type parameter. And as another type, of course, it's going to take in two arguments. So the function is going to need two formal parameters. Go and try that now, and when we come back, I'll show you my implementation. A quick example of a function template: the function is going to return the smallest of the two values. We do template the type name keyword between angle brackets, and the type parameter is going to be t for this example. Now notice, in the previous example we returned void. The previous print function template returned void, and this is going to return t. The function name is smallest, and I have two formal parameters, xp, which is also going to be of that same type, and yp, which is also of that same type. And this is going to return, using a compound statement, it's going to return the smallest of those two. If xp is less than yp, then return xp, otherwise return the y parameter. Okay, and in main, just as a quick example, I do cout smallest of 55 and 3. And of course, if I build and run, that prints out 3. And let's change 55 here to 2, for example, and build and run that again. And it prints out 2. And in a similar way, you can write a function template that returns the maximum or the largest value of two values. Another exercise for you, I'd like you to write a function template that is going to interchange, or in other words swap, the values of two variables that you pass in. This is my example. I have template name, and t for the type parameter. The function is going to be void, and I call the function interchange, simply because using switch or swap is going to conflict with existing functionality from the standard library. So you can use some other name. I simply used interchange here. And the trick with this exercise and the point of this demonstration is that you can do this. So for this formal parameter, which is called xp, this is going to be a reference to whatever that type is, and the same with the second formal parameter as well. So yp, that is going to be a reference to whatever that type is. In the body I do t, temp. Again, just demonstrating here that you can use t in the body of the function as well. In some of the previous examples we used it for the formal parameters, and we also used it in the return type, but you can also use it in the body. temp is of type t. Then I assign xp to temp, so the x parameter I assign that to temp. Then I assign the y parameter to the x parameter, and then I assign the temp local variable to the y parameter. And because xp and yp are references, the changes that we make in the body will be reflected in the main function. Scroll down here to main. I just have two random integers here, q and w. Q is initialized to 33 and w will be initialized to 55. Then I print those out, so q is q, w is w. And I do this print out here after the interchange just to make sure that we know, okay, we have invoked that function before we go and print those out again. Here I invoke the function interchange, I pass in q and w, which are variables, and then I print those values out again. Ctrl F5 to build and run. Q is 33, w is 55, and then after that interchange function invocation, q is 55 and w is 33. So that works as expected. You can also have function templates with multiple type parameters, so more than one type parameter. I have a quick example. Now for these examples we are going to use two type parameters, but this is a comma-separated type parameter list, similar to a comma-separated formal parameter list. So basically you can have as many type parameters as you need. Again, in this example I have two type parameters. I do the template keyword, the angle brackets, type name or class, t1, then I do a comma. Again, this is a comma-separated list. And then I do type name again, t2, for the second type parameter. Then I do the function definition, so I have the return type, the function name, and then I can use those type parameters in the formal parameter list. For this particular example, I have t1 for formal parameter 1, and that will be the type of formal parameter 1, and formal parameter 2 will be of type t2, so whatever type argument that type parameter accepts. Now again, note that return type can also be t1 or t2, or another type such as void, int, and so on. At this point I'd also like to note that type parameter names are by convention single uppercase letters, but you can follow your own conventions or your company's conventions. For example, instead of doing t1, t2, t3 and so on for your type parameters, you can use the letters tu, v and so on. A quick example on function templates with multiple type parameters. You can see I have template and then I have two type parameters, t1 and t2. I'm just using t1 and t2. You could have this be t and then this u, for example, and so forth. The next one v and whatever you want. Basically what I want this function to do is I want it to print out any two arguments that I pass it, so of any type, either types that I specify explicitly as here and as in the previous examples, or implicitly as we have here. So all this version of the print function is going to do is it's going to do cout argument 1 is, and then it's going to print out parameter 1. Then we do console output argument 2 and then parameter 2. I'll add these extra two statements just so we can see, okay, this is a new function call each time, so that we don't have all of these arguments right on top of each other. Okay, in main I call that print function. And how do I specify the types? Well, just like an argument list for a function, the main difference is the angle brackets and that we are passing in types. We pass in int for the first type argument, then comma, and then float. So in other words, parameter 1 is going to be of type int, and parameter 2 is going to be of type float. For the actual arguments, I pass in 33 and this float value here. So with this first statement, I explicitly specify the type arguments, whereas with these two statements here, they will be implied. The second statement, h is a character, so parameter 1 will be of type character, and then the second one is 55, so that's going to be an integer, right? The compiler is going to deduce that that is an integer. Parameter 2 is going to be of type integer. Then we have the third invocation of the print function. This is going to be a double, because we don't specify that to be a float as we do here. Again, parameter 1 is going to be of type double, and then we have a character here as well, so parameter 2 will be of type character, or char in other words. Ctrl F5 to build and run that. And let's see what we get. For argument 1 we get 33. These statements where I separate things out with these lines may be a bit messy. You can do something else in that way or just add extra space if you want. But we get what we expect here. Argument 1 is 33 and then argument 2 is 44.055 for that float. Then we call that function again, so we get argument 1 is h, argument 2 is 55. Then for the third invocation we get 55.55 and the character B. So this works as expected. Note once more that if I remove this if, this is going to become a double, but we are explicitly specifying that type argument here as a type of float. So if I build and run this will actually build and run, and you can just do Ctrl B to build too if you want, but you'll get a warning. I'll just switch over to the error list, and I can click here to show my warnings, and we'll get a truncation from double to a T2. And the reason we get that is this is a double, so the actual argument that's going to get passed into that function is a type double, but the function that's going to get generated by the compiler will specify this a formal parameter 2. The type of that will be a type of float, and so you'll get a truncation. It will work, you won't get an error, you'll get a warning, but of course you can lose some data in that way. Because if you remember, basically what happens is the number of digits to the right of the decimal point will get reduced. That is basically what truncation means. But if you do double right here and we Ctrl B to build, then we won't have that problem. That is basic stuff, I'm just reiterating that here. So what is the strategy for defining function templates? Well, what you want to do is you want to write a regular, in other words, non-template global or member function. Then you want to test, or in other words, debug that function, maybe with multiple types to make sure it works. And then finally, you'll convert the function to a template function. Okay, that is going to wrap up this video. In the next video, we'll look at what happens when we pass in our user-defined types, so our classes or structs, as type or template arguments to our function templates.